Depends on when you check it. Depends on when you check it. It takes almost an hour for it to.
Oh, I checked like in that.
Yeah, it looks like it. It looks like it's up. All right. Yeah, should work. All right, so lab this week's life tables. Monday and Tuesday I already went. Already learned how to do some life tables. Wednesday, Thursday, it's today, tomorrow. Bring a calculator. Monday's lab. I don't know if we probably didn't mention it, but on Blackboard, under our lecture, the lecture content folder, I have a handout that has all of the terms, all of the variables and definitions. So we go to this up here. Here's our course. Go to lecture, down at the bottom, life table terminology, opens up a PDF. This gives you all the variable names, definitions, has the equations that you can use to build the life tables. It's all here in one place that you can utilize. Also, hopefully you noticed that when you went to the lab, there was a YouTube video that shows you how to actually complete a life table. So after the lab, when you go to the homework part, if you still have questions about how did I do this column or how do we do this column, there's a how-to video that I walked you through. Can't remember what data we used. It could be the same type of data or it could be completely different data. I think it's completely different data. So that way it gives you a different example of how to create one of these tables. And we do survivorship curves and life expectancies. So everyone should know about that now. So this is where we left off. Logistic growth equation. We actually had left off with calculations. But quick review. So we had exponential growth equations, assumed we have a constant R. R doesn't change through time. We have instantaneous births and so forth. So we've got those 5 assumptions. If all those assumptions are met, we have our exponential growth. That's that R times N and also N times E raised to the RT. But we know that this exponential growth usually doesn't happen in nature. That's why we measure R, little r, when our population sizes are low. Because you have competition that takes place, you have other internal and external regulatory factors that limit growth of populations. So to model that growth, we have the logistic growth equation, where we have our exponential growth term, and then we have the term that's due to density dependence. And this term is basically adjusting our growth rate based on how close we are to our carrying capacity. So if we're far from the carrying capacity, we're going to exhibit close to exponential growth. If we're real close to the carrying capacity, our growth is going to be pretty close to 0. And if we are above our carrying capacity, we'll have negative growth. All right, and that's what we were talking about, the relationships, N versus K. Kind of gives us an idea of if we'll have population growth or population decline, or perhaps population stasis. With this equation, we know that we're going to see this increasing growth up to a maximum growth rate. And that maximum growth rate is at half of our carrying capacity. On our logistic growth graph, that is our inflection point. That's when our slope is getting bigger and bigger and bigger. We're going almost exponential. We're not. And then all of a sudden it flips and we start having slower growth until our growth hits 0 right at the carrying capacity. So with this equations, we did this example problem. And I asked you to have answers for these next two. So let's go through them. So what is the answer for this second one? What is the population growth rate when we have 500,000 cells in our vial? Big as we can get. What'd you get? How many actually did it? Good thing I didn't make a quiz for this thing. So, a problem specified R. It specified our carrying capacity. So the second part, what's our dN over dt if n is equal to 500,000? Well, we have our equation. We know our R. We know our n, what we start with. And then we have our density dependence term. So 1 million minus our 500,000 over 1 million. What do we get? Pull out the calculator and work it out. What's that? 0.5. For this, right? Yeah. It's 0.5. This part's all 0.5. What's our dN over dt? I think you missed that part.
Oh, I'm sorry. I thought you were asking about the other.
62,500. So if R is our cells per hour, at this point we are generating 62,500 cells per hour when we have a population size of 500,000. Now, as soon as we have one more cell, it changes. That's part of our instantaneous growth rate. So that's at 500 million. We then ask that second question. What's our dN over dt if our population size is 900,000? And we do the same thing. We use our equations. We have every term that we need. It is just substituting our values into that equation. Now, before you even answer it, should our answer be greater than this, 62.5, or less than that? What do you think? What's that? Less. Why? Because we're closer to the carrying capacity. What's the maximum rate of growth that we'll see in this population? This value. Why? 500,000 is half of our carrying capacity. That's the largest dn over dt that we will see. And we know that because when we did that first question, that 1,000, we had a population growth rate of about 250 cells per whatever unit, whatever time unit. So we expect it to be less than 62.5. What did we get? Is that what you get? 22,500. So yeah, the equations might seem scary, but it's not really. We have all the information that we need in the problem. It's going to be provided to us in the problem. We just have to know which equation we use and start substituting all of our values. So in this problem, we give a carrying capacity. A vial can hold 1 million yeast cells. We can say a habitat can support 1,000 individuals. That's all carrying capacity. If we have that carrying capacity, that clues it. That gives us clues that we're going to use this logistic growth rate. All right. So take a few minutes. Here's our quiz answers. Our attendance quiz. Push. All right, did you get it? Hopefully, no problems. Hopefully, no problems. All right. Put this back. So we do have additional homework. So under the problem sets, so lecture, problem sets, we had homework 2, that's practice problems. We've got practice problems for density dependence. So this will give you more practice. You can watch the YouTube how-to video that works through the problems, additional practice problems for you. And then we have this homework assignment. Again, extra problems. You can can work on it, and then there is a quiz tied to it that you'll basically go in and upload your answers. All right, you'll upload your answers to that. You won't have enough time to open up the quiz. The quiz is just the same questions. It's the exact same questions. It's just, again, round your answer to the nearest whole number. It's expecting whole numbers. So I have that due by the end of Friday. So that way, if you're working through it and you're stumbling on it, you can bring your questions to class on Friday morning. All right, it's homework 3. Homework 2 was due last night. I think I could look at it. So we asked you to have it done. So yeah, with the homework, we're not doing any like late fees or late assessment on it like the quizzes. I'm asking you to do it by that time, so that way it's fresh in your mind as you're working through it. So if we have questions, we could address it now before 2 weeks from now when we're working for the exam. So this even though it's a quiz, it counts towards your homework grade, which is 5% of the lecture. And you will see these problems on the exam. All right. Can you repeat it? I guess, Janelle, you were asking about due dates. Even though I set a due date, there's no late penalty if you do it late, and that's why you can have your 3 attempts for the homework. So work through it. If you have questions, if you're stumbling with it, then you can bring your questions to class on Friday. All right. So regulatory factors, like what are there out there? I keep mentioning competition because that's the common one. We're competing for the limited resources. That tends to, okay, hold on. The attendance code, please, Wi-Fi cut out. It was, the answers were the answers to those practice problems. So 22.5, one, and 62.5 was the other. So you should have those in the notes as we were working through them. That's our answer. Anyways, we talk about competition. That's an easy one to understand. But there are other factors that are out there, including density-independent factors. So these are the factors that regulate our population, but they do so without knowing what the density of our population is or what the population size is. So the regulatory factors are going to work in the same way if you have 1 million individuals, right, at our carrying capacity, or if you have 10 individuals. All right? So our density-independent factors are those population processes that are not affected by the density of our population. The best examples are weather and disturbances, because these things are going to affect our population regardless of how large or how small our population is. Right? You have a cold front, wicked cold front move through with a hard freeze. Who cares how many grasshoppers are out there? We're still going to depress our population sizes. These types of events are unpredictable in nature, usually unpredictable in nature. And this is going to add our randomness to the dn over dt equations. So our change in population growth rate, this is where our variation comes in, our variability. And when we have this type of variability, what we'll see is jagged growth. The randomness, these density-independent factors, starts to add our randomness to our population size through its effect on our population growth rate. All right? So if we look at a graph like this again, so where we have our rate, and this is birth rates or death rates, and we do it against population size, our birth rates and death rates are going to be constant because they're not going to be affected by our population size. This is a clue that we have density-independent factors regulating our population. Here's an example. We've got a log number of nests, occupied nests for a gray heron. Right? This came from our textbook, just to show how randomness can produce large drops in our population. In some cases, good weather is going to cause population booms. That's all unpredictable. It's all unpredictable. That adds noise to our population size graphs. So we've been talking about this regulation. What is regulation? So our population regulation is all of those mechanisms that determine our population size, and they do so through density-dependent factors. And so now when we have regulation, now we're going to control our population size, and it acts through our density-independent factors. So it's not our density-independent factors. Our density-independent factors adds noise. Our density-dependent factors will be regulated. So normally our density-dependent factors act as a negative feedback loop. And you've probably encountered something like this before in a previous biology course, or pretty certain chemistry covers it when we talk about competitors, enzyme site, and active site inhibitors. But here's how it works. So we have a population that's increasing. Right? It's showing growth. All of a sudden, density-dependent factors start to kick in. It's going to cause increase in mortality or decrease in reproduction. These two factors, or one of them, is going to cause the population to decrease. As our population decreases, we release our population from some of those regulatory mechanisms, and that allows our reproduction to go up and our mortality rates to go down. Consequently, our population increases, and it's just a loop. It's going to keep doing this until we get to our equilibrium point. And it's going to stay there until something bumps us off. Until something bumps us off. What is that something? Usually, it's going to be our density-independent factors. And that's going to cause us to add noise. So that's going to bump us up, either above or below, and then we're back to this, where our population increases or decreases based on our density-dependent factors. All right. So our density-independent factors are all about adding noise. All about adding noise. So let's look at some cases where you might see regulation and resets. I don't think I have it. Yep. So let's say we have a population that is being regulated. And we are at our carrying capacity. So through time, we have our population. If there's no density-independent factors, our population is going to be sitting right at there. Only our density-dependent factors. But what we typically see around that carrying capacity is our population size that fluctuates randomly around that point. So all of this jaggedness is due to those density-independent factors. And that's a common part, but that's not the only thing that we can see with our growth. In some cases, our density-independent factors act as a reset. So our populations may be growing up, I'm going to mark our carrying capacity here. It's growing up, it gets to carrying capacity, and all of a sudden we see this massive drop in our population size. Perhaps that's a weather event. So this is our density independent factor. Reduces our population size. And then our population size goes back to exhibiting our logistic growth, and then maybe another one happens. And then we go back. All of the jaggedness is our regular density independent factors at work, just the randomness of nature, of weather, of the conditions that are out there. But then we have a major density independent factor that all of a sudden causes a massive depression of our population size. What effect does that have on our communities? What do you think? So we're at populations. We're going to eventually get to communities. What effect do you think this has on those?
Probably like now.
Yeah, it could trickle down or trickle up. Depends if we have bottom up or versus top down control. So yeah, we have a population size that was near its carrying capacity. We caused a huge decrease in it. You're going to relieve some competition. If this population is competing with another species, you've just massively released that other species from competition or from predation, which allows this other population then to increase. So density dependent factors affecting that other species, but it's doing so through this population. So we can have our regulatory factors try to maintain our population near our carrying capacity. Our density dependent factors add the noise and have the potential of resetting our populations. All right. Summary for this one. No population can grow indefinitely. That's why we introduced our logistic growth equations. We have regulatory factors that are at work. They're going to be affecting our birth rates or death rates. They're going to affect our immigration and immigration rates. We know that. So that's why we introduced this density-dependent regulation equation, the logistic growth equation, to try to account for population growth with these density-dependent factors. What types of factors are out there that are going to regulate or affect our population growth? Well, we have biotic and we have abiotic factors. Right? So we have other organisms that are going to affect our populations. We also have just environmental conditions. They're going to act. These things can act in a top-down manner or they can act in a bottom-up manner. Now, you can have both occurring, top-down and bottom-up, but one's going to take precedence. It's going to be predominantly bottom-up or predominantly top-down. And then these factors are going to act either in a density-dependent manner or a density-independent manner. And the difference comes down to, is the strength and magnitude of their effect dependent on the population size of our species of interest. So for those density-dependent factors, the force, the magnitude, depends on how close we are to the carrying capacity. If we're close, it's going to be a pretty strong force that regulates us. It's going to be our density-dependent factors that try to maintain us near that carrying capacity. The density-independent factors don't really care what the population size is. They're going to affect our population size in basically the same way, whether we're at the carrying capacity or far from the carrying capacity. Now we should make a note that we are fluctuating here. All right? And in a sense, we could talk about this as being kind of like an equilibrium type point. But our conventional sense of equilibrium, which is that our population doesn't change at all, is just transitory. It's temporary. There's always going to be things that will influence our populations that produce the jaggedness so that our population size will always change. Either go up or go down. All right? Questions? I'll leave that up. Let me leave that up for you. Let's get the next. Got. Okay. Don't know how far we go. Trying to decide how far we go for our exam. That's how I was checking. I think. No, I think we'll have to. We might have some short days coming up. So we just finished this part. We do have a quiz. That is limits on population growth. I don't think this quiz has population growth equations. That's what the homework gives you practice for that. All right, so we will, that is going to go live. We will make that due Friday. Give you time to review it. Go. It is posted. 7.1 quiz, it's up. Due on Friday. So we're still talking about population growth. All right, and we've introduced regulatory factors. We introduced the density dependent factors, density independent factors. We're going to talk a little bit more specific on these for this next part. So it just kind of dawned on me. Didn't have 3 attempts on there. Equilibrium versus stability. We started kind of getting to this point. So equilibrium really has a meaning that we're going to be fluctuating, or we can be fluctuating. So the conventional definition of equilibrium is that it's not changing at all. And we're going to say that just doesn't happen. All right, contingency in ecology is not going to make that happen. So for ecology, when we refer to equilibrium, it means that our population is going to be maintained near our carrying capacity. All right, and it's going to be maintained near that carrying capacity through the density dependent factors. We're not saying we are completely at it, but we are near it. So in our graph, we've set our equilibrium. We have fluctuations. We're going to be bouncing around it. That's our uncertainty, the randomness, stochasticity of weather, and so forth. But since we're fluctuating right around that carrying capacity, that's our equilibrium. We can say that our population is in equilibrium. Now, this equilibrium is a special case of population stability. So the broader term is stability. And stability is just saying that our population is going to be fluctuating within narrow limits, within some limits. And we could say, well, hold on, this is fluctuating between here. Yeah, that's not narrow limits. You can see that when we get near our carrying capacity, we're fluctuating around them, and then we have a massive drop, and then we're still growing through this section. This is not stability. All right, so our population stability is just, we're maintained within limits. but we don't need to be near our carrying capacity. If we're near the carrying capacity, then it's a form of population stability, but it's also equilibrium. And that's why I say equilibrium is really just a special case of population stability. Usually, if we're not going to be at our carrying capacity, our population is going to be maintained at some range or some band, some limits below our carrying capacity, usually. Why does that happen? What maintains this? Well, usually it's going to be a combination of our density-dependent factors and our density-independent factors. So remember, our carrying capacity is determined by the resources that are available. Right? How many individuals can all of our resources support? That's our carrying capacity. Once we start building in and factoring in predation, then, and perhaps competition, then we're going to start producing a different equilibrium point. And that's where our stability comes into place. So our density-dependent control doesn't always produce stability. And the great examples are predator-prey interactions. You would think that once we introduce a predator, the predators are going to grow, their population size is going to stabilize, and it's going to maintain our prey populations at a certain level. That's an ideal case. But we don't normally see that. What we typically see is that both the prey and the predator populations fluctuate, and they're out of sync. So as the prey populations increase, our predators are still down here at our population size. And then the predators see a bunch of food supply. And then their populations increase. And as they increase, now they start causing a crash in our preys. And once those crash, well, hey, we run out of food for the predators, those populations crash. So that's what this is. Snowshoe hare populations, which are prey items of the lynx. And what we see, we've got different numbers here, so thousands of hares and then thousands of lynx pelts. All right, these are trapping records. So just they're not necessarily numbers that are out in nature. It's what are the trappers and the hunters bringing in. But what you can tell is as the number of pelts changes, that's a pretty decent reflection of our population size. Question, are these pelts, are these actual population sizes, or is this more of an index of relative abundance? What is an index of relative abundance? That's prepping for final exam. What is index of relative abundance?
Where you use like evidence, indirect evidence to estimate a
Yeah, where we use indirect evidence to estimate our population sizes. And we don't have like a hard estimate. Like we can't go out and say, yeah, there's 1 million hares out there. But what we can do is based on the number of pelts, we can say, yeah, when we have a lot of pelts, we're going to probably have a larger population size out there than when we're down here with few pelts. This is a great example of a relative abundance, index of relative abundance. So that's what these are. So you see the hare populations, they increase, and it's not until we get near the peak when we start seeing the lynx populations increase, right? Relative populations. All right, and then once the lynx populations increase, get to start increasing in size, they cause a crash in the hare population. Once that crashes, it allows the hare populations to increase. That provides more of a food source for the lynx. They start taking off. They cause a crash of the hare populations again, and it repeats itself. So this is a case where we don't really have stability. We've got stable fluctuations, but we don't have a stability where we're fluctuating around some set number. These predator-prey interactions are actually fairly interesting because we can utilize equations that predict how our population should cycle. All right, so just like our logistic growth equations, we can make these equations to predict the cycling. When a guy went out and tried to test those, it always failed. His populations always crashed, no matter what. So until he started adding more and more escapes for the prey population. And it gave them enough time to where he started saying a few cycles of the predator preys, like this, like what we have up here. But then eventually it crashes again. So it's an older paper. They did mites and spiders, and the habitats were basically oranges. And he had little bridges, like little toothpicks, that allowed the mites and the spiders to move between different habitat types. I think we'll talk about those again. All right. So what we're going to do is we're just going to stop here. I know I'm ahead. Really do have to figure out how far we go for this exam, for this next exam. So we're going to stop here. So looking ahead, we're going to talk about internal regulatory factors. So factors internal to the population that will regulate the population. Then also some of the external factors. So I do have the quiz. So practice the homework, logistic growth. You can upload it. If you have questions, bring your questions to class on Friday. And the homework, the official due date of that homework assignment will be due that week before the exam. So that Monday, so that way I can post the key. Yeah, the key. All right. Let's call it quits today.